This is Dr. J. Mohan from EC Department, Institute of Aeronautical Engineering. Today we are going to discuss about the Fourier transform section 4 in the topic of signals and stochastic processing. Last session we studied for the 13 properties. It's like linearity, time reversal, time shifting, and time differentiation, frequency differentiation. Like this one we studied for the around 13 properties of Fourier transform. This session we should go for the possible theorem of Fourier transform and a possible identity of Fourier transform and example of Fourier transforms. This is the last session for the Fourier transform. Okay, first we go for the possible theorem of Fourier transform. The statement that Parseval's theorem, the energy of the signal x of t is a periodic signal, or power signal x of t, if x of t is a periodic signal in the time domain, is equal to the energy or power in the frequency domain. So that means if you take for the signal as a aperiodic signal, the signal is represented as energy, then its produce a Fourier transform in the case is equal to energy in terms of time. If the signal is a periodic, if the input is x of t is a periodic, the signal produces a output as a power in a frequency in Fourier transform. It's called Parseval theorem. In this Parseval theorems, I should take for the input as two. One is x1 of t and another one is x2 of t. We should take for the Fourier transform of input, it's produced for the x1 of omega and x2 of omega. Here I mention, we take for the time domain of x1 of t to do for the Fourier transform. We got for the frequency domain of x1 of omega and another signal I should take for x2 of t. We should take for the Fourier transform. It's produce the frequency domain of x2 of omega. As per the statement of Parseval theorem of Fourier transform, if we take for the two inputs in the time domain as a periodic and a non-periodic signal, if the periodic, it's going to produce for the energy of it's produced for the power of in frequency domain. If the signal is aperiodic, the Fourier transform is produced for the energy in the frequency domain. So due to that case, I should take for the two signal, one is represented as x1 of t, another one is represented as x2 of t. x1 of t, I doesn't change anything, but x2 of t, I make to do for the complex conjugate value, because of we need to prove for the Parseval statement. Both the signal we should take for the periodic or aperiodic status. If we take for the periodic, the signal is represented as a power signal. So that power signal, if we are going to give for the input of Fourier transform, that is x of t, in the Fourier transform, it's produced for the power of frequency domain in the both the x1 as well as of x2 of t. That means x of t in the sense x1 of t and x2 of t. Both is represented as a periodic, then it's produce the output as a power in the frequency domain. If you take for the aperiodic signal, that is going to give for the input as x of t, it's represented as a energy. So that will produce the output as frequency domain in the energy term. So due to this condition, I take for the x1 of t and x2 of t is complex conjugate values. Now I should do for the Parseval theorem statement, the integration of minus into plus into x1 of t and x2 of t I take for the complex conjugate with differentiate with dt. its produced output is equal to 1 by 2 pi integration of minus infinity plus infinity x1 of omega x2 star of omega d of omega. Now in this case, x1 of t and x2 of t are the complex functions. This means what is it? So we take for the case of periodic and aperiodic, the signal is represented as a x1 of t and the complex value of x2 of t. Its produced output is a frequency domain of case. Frequency, the periodic in the sense is a energy, it's a power signal. So the output of Fourier transform also power, but in the frequency domain. So input is a time domain. So that's why generally I call for both x1 of t and x2 of t is a complex function. But here we are taking for the x2 of t complex. Even you take for the x1 of t complex, you don't take for the x2 of t as a complex. Anything. So if you take anyway, then its produced output is represented as a power or energy based on the given signal of input in the periodic or non-periodic condition. We need to prove for the Pascal relation. The statement we know, the Pascal statement, the integration of minus infinity plus infinity x1 of t, x2 star of t dt. That is x1 of t and x2 of t are the complex signals. Then its produced output is represented as a 1 by 2 pi integration of minus infinity plus infinity x1 of omega, x2 star of omega, d of omega. From the definition of inverse Fourier transform, we know the inverse Fourier transform, that is called for the Fourier transform inverse of x of omega, capital letter x of omega is equal to x of t, that is small letter x of t. This x of t is equal to 1 by 2 pi integration of minus into plus into x of omega e power plus j omega t d of omega. This equation we should adapt for the proof of Pascal relation. Now in this case, I take for the x1 of t. This is x1 of t. I should take for the x1 of t. As per the statement of Pascal relation, here x1 of t is there. This x1 of t I should take for the inverse Fourier transform equation. So the inverse Fourier transform of x1 of t is equal to 1 by 2 pi integration of minus infinity plus into x1 of omega e power j omega t d of omega. This value we should substitute for here. So after substituting, we got this equation. So what is it? Integration of this integration doesn't get to change. First integration of minus infinity plus into then x1 of t, that is equal to this value 1 by 2 pi integration of minus infinity plus into x1 of omega e power j omega t d of omega. This x2 star we keep same as like that one, and d of t remaining we keep. So this case, this two portion, okay, this two portion is going to have the constant. We take it out from the this equation. Okay, so then at the same time, by interchanging the order of integration in the right side of our equation, we should write this expression as like this form. Okay, so what the case? This portion we should take it out. Yeah, this portion we should take it out from the right side. 1 by 2 pi integration of minus infinity plus infinity x1 of omega. Remaining portion, the integration of minus infinity plus infinity of this integration. Then this portion as well as of this portion. All I should write like this form. Integration of minus infinity plus infinity x2 star of t e power j omega t d of omega. Now this portion, what I'm doing here only is going to have the star. I take it out for the whole star here. Automatically what will be happen? Here we represent by the minus, this star is removed. Okay, then I rewrite for that equation. So this right side of equation 1 by 2 pi integration of minus infinity x1 of omega, I keep same as like that one. I take it out for the star. Here is changed for the minus. Okay, x2 star is there. That star, that is complex value. I take it out. Here e power value getting to the minus d of omega. Now you can see these terms. What is it? This is integration of minus infinity plus infinity x to e power j omega t dt is that. What is it? E power j omega to dt. So we know the Fourier transform of x of t is equal to x of omega. This value is equal to integration of minus infinity to plus into x of t e power of minus j omega t dt. So this term is represented as x of omega. But we here using for the x2 of t, just you can write for the x2 of t, then this is called for the x2 of omega. Okay. So one more thing, it's have the whole star. So this star in the equation, in the partial case of right side, star is there. This star I keep for the whole star here. So this automatically what will be happen? Capital letter x2 star of omega. We wrote like this one. So now I should write for the this term as x2 omega star. I write complex conjugate. So now I write for the right side of our equation is equal to 1 by 2 pi integration of minus infinity plus x1 of omega is as usual. This term I should write for the x2 star of omega. Then d omega is that I write here. Okay. Now you look for this equation. What is it represent? If you take for the Pascal relation of integration of minus infinity plus infinity x1 of t, it's and x2 star of t d of t is equal to 1 by 2 pi integration of minus infinity plus infinity x1 of omega x2 star of omega d of omega. Now the left side as well as the right side, both the side of Pascal relation is getting proved. Okay. Now in this case, the Pascal statement I should write for the minus infinity to plus infinity x1 of t x2 star of t d of t. That value is equal to 1 by 2 pi integration of minus infinity plus infinity x1 of omega x2 star of omega d of omega. Now the Pascal statement is getting proved. Okay. This is called for the Pascal statement. In this case, if we are taking for the x1 of x2, x1 of t and x2 of t as a both signal is represented as a complex case. If as a periodic, then the produced output also periodic. All periodic signal it's going to satisfy for the power only. So the output side also getting to the power. That means if we take for the time domain doing for the complex conjugate value of power signal in the periodic condition, the output also we get for the power but in the frequency domain. At the same time, if you take for the aperiodic signal in the x1 of x2, x1 and x2 of complex case, you take for the Pascal relation, the producer out case is represented as an energy signal, but in the case of frequency domain. So that means, as per the Pascal relation, if we take for the x1 and x2 complex value of the signal, if the signal is periodic, it's going to satisfy for the power. It's produce the output also it will be represented as a power even though it's in the frequency domain. But in the case of input case is time domain. If the signal is represented as a aperiodic signal in the time domain, it's produce the output of Fourier transform is represented as a energy in frequency domain. Okay, this is called for the Pascal relation. Next case, we go for the Pascal identity of Fourier transform. In this case, we take for the Fourier transform of the energy content of the signal x of t. That means is represented as a aperiodic signal. In the time domain, we take for aperiodic signal. Those case, the energy is equal to integration of minus infinity plus infinity mod of x of t whole square dt is equal to 1 by 2 pi integration of minus infinity plus infinity x of omega mod square d of omega. So now mod of x of t square is represented as a x of t into x star of t. This means x1 of t is equal to x2 of t equal to x of t as a possible statement condition. If the time domain, both the signal is represented as a periodic, in the time domain case, the signal is going to satisfy for the energy and produce the output also is represented as energy, even though the signal is represented as a frequency domain. So that condition we take for the Parseval identity of Fourier transform. The Parseval identity of Fourier transform state that energy content of the signal x of t is the energy is equal to integration of minus into plus into x of t whole square d of t. Now this is called for the energy. Its produced output is represented as 1 by 2 pi integration of minus into plus into x of omega whole square d of omega. So this is also energy, but in the case of frequency domain. So the input side, it's represented as a energy signal. If you are going to give in time domain, you take for the Fourier transform, it's produce the output also, it's represented as a energy, but in the case of frequency domain. This is called for the Parseval identity. This condition, both x1 and x2 is equal to x of t as in the Parseval relation. Now, the Parseval identity is also called as energy theorem or Rayleigh energy theorem. The quantity is x of omega mod square is called as energy density spectrum of the signal in time domain. Okay. So now this is going to give for the two cases. One is Rayleigh energy as well as this is if we Parseval identity is going to give for the energy spectral density, that is EDS of the signal in the time domain cases. Now this will be seen in the probability density condition in future topic. Now we go for the proof of Parseval identity. As per the statement, we take for the x1 of t and x2 of t in the Parseval theorem. Now the x1 of t and x2 of t both are equal. That's why I take for the generally x of t in time domain. The energy of the signal, as per the formula we studied in the first model, energy value is equal to integration of minus into plus into x of t mod square dt v root in the continuous time case. Now this x of t is represented as x of t and x of t star. So one is x of t, another is a complex conjugate value. This notation I should substitute here. So x of t mod square I represent for the x of t int x star of t dt. This value is equal to 1 by 2 pi integration of minus into plus into x of omega x star of omega d of omega. You write. Okay. So how we may go for this one? So we go for as usual our Parseval relation statement only. So in this Parseval relation we taken for the inverse Fourier transform. So we substitute for the x of t is x of t as a inverse Fourier transform of x of omega. That value is equal to 1 by 2 pi integration of minus into plus into x of omega e power of plus j omega t d of omega we take. So instead of x of t we should substitute for that values, this value. Then we take it out for the portion of right side. We take for the integration of minus into plus into as a energy condition. What is that? X of t, in terms of x of t, I should substitute for 1 by 2 pi integration of minus into plus into x of omega t power minus plus j omega t d of omega into x star of t d of t I should write. Now, so this term I take it out. Integration of minus into plus into here 1 by 2 pi x of omega we take it out. What the remaining term is that? So integration of minus into plus into this term and x star of t e power of j omega t d of t and I take it out the d of omega. This term I combine. So now this term I should write as 2 pi integration of minus infinity to plus infinity to x of omega. Then I write as a minus infinity plus infinity x of t e power of minus j omega t d of t whole star. This star I take it out for the whole star here. Then d of omega. What is it value? This one. If you take for the whole star, this value is represented as a x of omega. This star it will be going to happen here. Now I should write this equation as 1 by 2 pi integration of minus infinity plus infinity x of omega. This is x star of omega d of omega. This d of omega it's similar. Now this two term I should write as a x of omega mod square. Now finally what will be going to happen for our equation? In the right side of Parseval identity, this value I should write here 1 by 2 pi integration of minus infinity plus infinity mod of x of omega square d of omega. This value is equal to integration of minus infinity plus infinity x of t x star of t d of t. Now the Parseval identity is getting to prove. That only I should write here. See, so instead of x of t, here I substituted for the inverse Fourier transform of x of t. Then here I take it out for the common terms, that is 1 by 2 pi integration of x of omega. I take it out. I put for this x star of t into e power plus j omega t dt. Then I take it out for the star. Then finally we got for the Parseval identity statement. Now Parseval identity statement is getting to proved. Okay. So therefore the signal of Parseval identity in the time domain of energy case, the integration of minus infinity plus infinity x of t mod square d of t is equal to 1 by 2 pi. That means Fourier transform 1 by 2 pi integration of minus infinity plus infinity x of omega mod square d of omega. We should prove. This is called for the Parseval identity cases. Next, we take for the some example. Find the inverse Fourier transform of the function f of omega is equal to 12 plus j omega minus of omega square divided by omega square minus 2 j omega minus of 1 and minus omega square plus j omega minus of 6. In this case, I am going to using for the factoring each of the quadratic polynomials we have. This term I should make for the, that is numerator term I make for the single j omega condition. So I can split 3 plus j omega and 4 plus j omega. Okay, this both we multiplied, we get for the 12 plus j omega, that is 7 j omega minus of omega square. This 7 j omega I split for the 4 and 3. So now due to that case 3 plus j omega 4 plus j omega we got. So this one is represented as a numerator. Same like that one I should do for the denominator also for this equation. That means factoring quadratic polynomial condition. So this two term I should write as a 1 plus of j omega whole square. This term I should write as a 2 minus of j omega into 3 plus of j omega. Okay. Now what will be, you can compare with numerator and denominator. This 3 j omega, 3 plus j omega, this 3 plus j omega getting to cancel. What the remaining portions are there? 4 plus j omega divided by 1 plus of j omega square into 2 minus of j omega is there. I should write here. Then after I make to use for the polynomial condition a divided by 1 plus of j omega square plus b by 1 plus of j omega plus c by 2 minus of j omega. Now I should find for the ABC. A, B, C. So if you need to find, then I make to do for the cross multiplication. So only I should take for the upper part, that is numerator part. 4 plus of j omega I should write here. Okay. This term I make to do. So A, okay, A into, already it will be the 1 plus j omega is there. You can limit. Here also 1 plus of j omega. Remaining portion is represented as 2 minus of j omega plus B multiplied with this 2. B, what is it? 1 plus of j omega into 2 minus of j omega. So that 1 is getting to cancel. So remaining case C, we can see what is it? It will be have the 1 plus of j omega, then 1 plus of j omega is there. So 1 is going to remove. That's why I represent as a 1 plus of j omega whole square. This is plus. Now this portion is divided by this whole term, 1 plus of j omega square, 2 minus of j omega, then 1 plus of j omega is that. So this is equal to this term, 4 plus of j omega divided by 1 plus of j omega square, 2 minus of j omega square. So this term, it will be repeated. That's why you can remove for 1 plus of j omega. Now these two are getting to cancel. What the remaining portions are there? This portion and this portion. That portion only I wrote here. 4 plus of j omega equal to A, 2 minus of j omega plus B into 1 plus of j omega into 2 minus of j omega plus C, 1 plus of j omega square. Now I need to equalize for the ABC. So here is 4 is there in the constant. Here term you can see the 2A. Here is represents a 1 into P into 1 and B into 2. That means both will be going to represent is B 2B. Then this term is equal to 1. So like that one I write for all. So J term we can take for the J term, can multiply, and J term is equal to 1 equal to 1 minus of A plus B plus 2C. Then we go for the 0 term, that is represents there is no number, that case 0 is equal to P minus of C. Based on this term, I should find for the ABC. The A value is equal to 1, B and C value is equal to 2 by 3. Now it will be substitute for this portion. Okay. So now you can substitute for the case of the portion. If for A greater than 0, we have Fourier transform of A e power minus at u of t is equal to 1 by 1 plus of j omega. See here, what is it be represent? So here is 1 plus of j omega whole square, a divided by a we know that is equal to 1. Then b we know 2 by 3, 1 plus of j omega. C we know that is also 2 by 3. So we should go for the Fourier transform condition, that will be going to satisfy for the single direction exponential condition. So that's why I take for that formula, single direction exponential condition is Fourier transform of e power minus at u of t 1 by 1 plus of j omega. Another case, Fourier transform of e power at u of minus t, that is a negative direction of your unit signal, 1 by 1 minus of j omega. Another case, if we multiply with the t of e power at u of t, that is represented as a differential case of formula, that is 1 by 1 plus of j omega square, where u of t is called for the unit step function. Thus by the linear of Fourier transform, I should write from this equation. Okay, what is it? This equation, what is it? A divided by 1 plus of j omega square. That means I should take for this term. Okay, so the A we know that A is equal to 1. We find A is equal to 1, we find. So now the 1 into t e power of minus t u of t I should wrote. Okay, this term is equal to A equal to 1 by 1 plus of j omega whole square. Okay, so here see we make to write as A is equal to 1, that is A divided by 1 plus of j omega whole square. The a value is equal to 1 now. You can substitute for the a value is equal to 1 here. Then e power t into e power of 1 into minus of t u of t I wrote. Another c b is equal to 2 by 3. Okay, b equal to 2 by 3, and even though the b term is represented as a 1 plus of j omega. What the 1 plus of j omega here? See the 1 plus of j omega. This is going to satisfy a plus of j omega. Then I write as here 2 by 3 e power of minus t u of t. Then another term 2 by 3 e power 2t u of minus t. Finally, I wrote when t is greater than 0, t plus of 3 by t plus of 2 by 3 e power of minus t. These two terms I should combine. Okay, so sorry, I should combine for these two terms. So t, I take it out the u of t. Remaining portion t plus of 2 by 3 e of minus t is there. Take it out when t is greater than 0. This is u of t. This is also u of t. If we go for the minus u of t, that is lesser than value of t lesser than of 0, then I take for this one. Okay, u of t is minus. That is a minus direction up to infinity. 2 by 3 e power t. So finally I wrote the equation x of t, that is x of t or f of t is equal to t plus of 2 by 3 e power of minus t multiplication t is greater than or equal to 0. Then 2 by 3 e power of 2t t less than 0. This equation we got. This is represented as inverse Fourier transform condition. Next, we take for the another case of the same condition. For x of t is equal to u of t e power minus of t, and find y of t, where the differential equation d square y of t dt square plus dy of t dt minus of 2y of t equal to x of t. So here they given for the differential equation and input. In this condition, they given a always greater than of 0. That means it's represented as a positive. We have the Fourier transform. We know the Fourier transform of e power at u of t is equal to 1 by a plus of j omega, and Fourier transform of e power at u of minus t is equal to 1 by a minus of j omega. If you take Fourier transform of both sides of differential equation as what we are going to receive from sum, we got j omega square y of omega plus j omega y of omega minus 2 y of omega x of omega. Okay, so this we studied. That is called for the differential equation. So differentiate with t of x of t. You take for the Fourier transform. It's represent for the multiplication with j omega into x of omega. Okay, this is time differential property we studied. In this time differential property only we going to adapt it for this given differential equation. Now this is a one differential cases. If you have the multiple cases, that is Fourier transform of d by dt power n d by x of t is equal to Fourier transform of j omega whole power of n x of omega we wrote in the differential equation. So now the 2 time is going to differentiate. That's why this is 2. I write for the j omega square of 2 y of omega. The term is represents of y of t. That's why I write for the y of omega. Next, one differentiation j omega y of omega minus another one is there is no differentiation then 2 y of omega. If we take for the Fourier transform, this whole term I should take for the Fourier transform to adapt it for the differential property. Now you take for the this term as a Fourier transform. Okay, what is the Fourier transform of u of t e power minus at? That is equal to we use for this equation Fourier transform of e power at u of t 1 by a plus of j omega. Now A is present for the 3, that's why I write as a 1 by 3 plus of j omega. We should write. So in this term, we take it out for the y of omega. For the y of omega, we take it for the y of omega in outside. This is capital letter. What is it? J omega square plus of j omega minus 2 is there. This value is equal to 1 by 3 plus j omega, that value x. Okay. So just I need for the y of omega. Then I write for like this term. Okay. So that is represented as system cases. Now this term it's go for here. So 1 by 3 plus j omega that is j omega square plus j omega minus 2. I should write for like this term. Okay. So j omega minus 1 j omega plus 2. So now I should apply for the partial differential cases. This is a by 3 plus j omega plus b by j omega minus 1 plus c by 2 plus j omega, I write. Now this based on this case in partial differential cases, I need to find for the ABC. I do for the cross multiplication. The value is equal to 1 for the right side. Left side we have the combination of ABC. At the same time, in this case, I multiply inside of all the signal. Then what the omega case and what the j omega, what the 2 omega. For here, omega is represented as a, that is minus 1. Here is also minus 1. B term is minus 1. C term is minus 1. So like that one, I can split. Then A plus B plus C is equal to 0. A plus 5B plus 2C equal to 0. Minus 3A plus 6B minus 3 is equal to 0. I can simplify for this one. Then I got for the A is equal to 1 by 4. B equal to 1 by 12. C equal to minus 1 by 3. Now we need to substitute for here. A value, B value and C value. We know this is, we take for the A divided by 3 plus j omega. A by 3 plus j omega. A we find. A is equal to 1 by 4. Substitute here. A equal to 1 by 4. So we take for the Fourier transform. That is called for the inverse Fourier transform. So what is that? 1 by 4. For as per the C here, you take for the 1 by a plus of j omega in terms of this is e power minus at u of t. So now what will be happen? 1 by 4 is there. Then u of t automatically is k. Then 3 plus j omega e power of minus 3t. Now this is the term of first case. Okay. This term. Another case. Fourier transform of inverse. Then b is equal to 1 by 12 divided by, you take for here b j minus 1, that is minus 1 plus j omega, I write. So this term is equal to 1 by 12 I should take. Here I have the minus, that's why e power of plus t, u of minus t I write. Okay, so like that I do for the another case of C. The C term. C we know the C is equal to 1 by 3. Then here I have the 2 plus 2 is there. That's why I should write as a e power minus 2. That value equal to 1 by 3 u of t e power of minus 2t. You can add for all. We got for the output. That output is equal to this term. Y of t is equal to 1 by 4. U of t e power minus 3t minus of 1 by 12 u of minus t e power t minus of 1 by 3 u of t e power minus 2t. Okay, this is the solution of the differential equation when you are going to receive for the input. Okay, next case. We take for the an LTI system as impulse response, that is equal to h of t is equal to e power minus 3t u of t. What was the input x of t when the output is e power minus 3t u of t minus of e power minus 4t u of t. So we got for the h of t, that is system function, we got for the output also. That means this is a LTI system. We given for the input its produced output is y of t. This LTS system response is called for the h of t. Now y of t is equal to x of t into h of t. Okay. So in this sum, they given for the h of t and they given for the y of t also. Both the response they given. We need to find for the x of t. So that is represents the sum. Okay. This condition I should take a is always greater than 0. We know Fourier transform of exponential condition in the one side case e power at u of t in the Fourier transform is equal to integration of minus plus into e power minus at u of t into e power minus j omega t dt, the Fourier transform. Then after we do for the u of t is there, that's why u of t is present but the signal is 0 to 1. That is the signal, this is infinitive side in the t, 0, it will be go for only this direction. That minus direction is represented as 0, minus into direction of t, then this is 1. Okay. So the amplitude is equal to 1, that is u of t. We call for the u of t. So the signal is present for the 0 to infinity only. So that's why integration is present for the 0 to plus infinity. E power minus t, I simplified, e power at a plus minus plus j omega dt. We can make to integrate and substitute the limit. We got for the 1 by a plus of j omega we got. So that's why I write for the last example also. Fourier transform of e power of minus at u of t is equal to 1 by a plus of j omega we wrote. We got this equation. Now we need to find for the x of t. That's why what we are doing. Then we got for the system function, we got for the output function. So we take for the Fourier transform for both the time, both the case of system function response as well as of output response. If we take for the Fourier transform of h of t is equal to, as per the statement of this condition, that is Fourier transform of h of t is equal to Fourier transform of, what is the h of t? E power minus 3t u of t. That value is equal to, so a is represented as 3 now, that is 1 by 3 plus of j omega. So here I wrote h of omega equal to 1 by 3 plus of j omega. At the same time, you take for this one also for the output response. So what is this for the, if you take for the Fourier transform of this portion, for the output 1 by 3 plus of j omega. So this one is represented as a minus of 1 by 4 plus of j omega. Here I write for here. Okay. The term here is minus, that's why I use for minus here. So now we got for the frequency domain function of h of omega and y of omega, both the condition. Okay. So now we know the system response. The system response is equal to y of t is equal to x of t into h of t. Here I wrote y of t is equal to x of t into h of t. To take Fourier transform for this one, what we have got, this side also Fourier transform, left side or right side. This is y of omega, capital letter omega, capital letter x of omega into h of omega. We got. See, I wrote here. So y of omega is equal to x of omega into h of omega. But this case, we don't know for the h of x of omega. We know y of omega and h of omega. We substitute for both. So we substitute for the both. Then finally we got x of omega equal to 4 plus of j omega. I should write here. So I need for the x of omega. Y of omega we know. What is that y of omega? Y of omega equal to 1 by 3 plus of j omega into 4 plus of j omega. You know how to got. This is make to cross multiply. So if we make to cross multiply for this one, we got for the 4 plus of j omega minus of 3 plus of j omega. This minus is common. If we go for inside here, okay, Here is represented as 3 plus j omega into 4 plus of j omega. This 2 are getting to cancel. 4 minus of 3 is equal to 1. I should write the term is represented as 1 by 3 plus of j omega into 4 plus of j omega. So that is equal to y. Now we need for the x. This term we take for this term. We need for the x. The x is x of omega is equal to, this is go for this side of right side in the upper case. Sorry, upper. What is that? We got 3 plus of j omega divided by 3 plus of j omega into 4 plus of j omega. These two are getting to cancel. So finally what we got? We got for the x of omega equal to 1 by 4 plus of j omega. Now you take for the inverse Fourier transform. Fourier inverse transform of x of omega is equal to x of, small letter x of t. X of t. If you take for the inverse Fourier transform of this one, e power minus 4t u of t. So here I write. So now if you got for any signal as like a system response signal or output signal or input signal, we should convert through the Fourier transform also. Here I take for the LTE system. For next example, calculate the Fourier transform of the function del of t is equal to 1 minus of 2 mod of t. The mod of t is going to present for the less than of 1 by 2, 0 otherwise. I should take for the input is x of t is equal to 1 minus of 2t, 0 less than of t less than of 1 by 2, 0 otherwise. So we know del of t, here I write as here z of t plus z of minus t. This is represented as a linear and time reversal property of Fourier transform. If we take for the Fourier transform, we got for the Fourier transform as a f of omega equal to z of omega plus z of minus omega. Now you take for the z of omega is represented as a minus into z of t e power minus j omega t. We should substitute for the this z of t here. Then you can substitute the interval. After doing the integration, substitute the interval of 0 to t by 2. Finally, we got for the output is 2 minus of j omega minus of 2 e power j omega 2 divided by omega square. Then we can simplify for the equation. Finally, we got the output is sin c square omega by 2 omega by 4 divided by 2. Then sin c is equal to sin x divided by x. Up to this much, I am going to stop my presentation of Fourier transform session 7. These are I referred from the signals and system and the signal communication of D. Latik and open up. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.